Boom. Fine. Hey, Kevin. Singman.
Hi, David.
Let's give folks one more minute to
Yep.
settle in, I guess. Singman, quick question. When I commit a update to any of the designs, do you receive email sometimes?
Oh, yes.
Okay. All right.
Yeah. Last time I received an email from Gmail. Yeah.
Okay. I wasn't sure if that part is working. Okay. Let's get started. I guess we'll do a quick update. We had a discussion last week at the POC meeting how to set up the power tree for our design. And I think what we are going to do is we are gonna go with IVRs embedded in basically IVRs on the substrate. We'll place the IVRs just under the chips because we're looking at about 400 watts of power and having the IVR in the on the package. That seems like a new emerging technology, so it will just make the whole design more interesting. So the idea would be we are going to assume that we're bringing 48 volts in the board, and on the board we'll do a conversion of power from 48 to 12 and then from 12 to 5, and then 5 goes in the package, and basically there will be a few IVRs to deal with the HBM power supplies for basically all HBM instances, and then IVRs for the UCE supplies, and then for the CPU core. So we're going to have a few of those, but that would make the whole design a little bit more interesting. Additionally, one thing, right now our system really doesn't talk to the outside world, right? We have the CPU chiplets and we have the HBM chiplets, and they all talk to each other. So to kind of make it a little bit more realistic, I have created a kind of a placeholder for IO chiplet that has UCE on one side and PCIe on the other side. For the IE the way I set that up is for two UCAEs. We are assuming that UCAEs work at 32 gigabits data rate. So for two UCAEs, I have one PCIe, assuming that it runs at 200 gigabits, and one UCAE. Basically, I misspoke. So it's one UCA instance, but it's going to be by 16. So my mental calculation was that this basically is going to match the bandwidth on both sides. I should probably redo that because I didn't do it on paper. I just did it in my head and would have gotten it wrong. But that's what the setup is for now. So yeah, that's on my side, and Sigmund has some nice updates too. Sigmund, why don't you go ahead and give us your update?
Oh yeah, of course. Just a second, please. Let me share my screen first. Yeah. Do you see my screen?
Yep.
Yeah, so last week I had an issue on the on the eye diagram. So eye diagram was originally not open enough, but so I've changed the distance between the chiplets to 500 micrometer from 2000 micrometer or 2 millimeter, and the result is shown like this. Yeah, and the line within spacing is 1 micrometer and 3 micrometer. So now we have opened completely opened eye diagram, and this satisfy the UCA requirements.
Yeah.
And yeah.
Second quick question, actually. Does ADS have the capability to draw what the target open eye width and height should be? You know, kind of draw a small rectangle in the middle showing what the target is, so that we kind of have a visual clue about how good this result is.
Oh yeah. Of course. Yeah, I think I can draw the rectangular here.
Yeah,
Nah.
okay. I meant it more like apart from drawing a rectangle on top of a graph. Is there any way to specify what your target is, and it will automatically show you the rectangle?
Um, I have no idea for now, but
Okay.
I have to, yeah, take a look at the
Okay.
options.
Okay. Yeah. So, one thing about these results,
Mhm.
we should add this to your presentation for the global summit.
Mhm.
Right. Those results which you are generating, see how you can add them. And for that one specifically, it would be good to have that rectangle in the middle so people get
Mhm.
feel of how good is this, right? Because
Mhm.
not everybody would be familiar with exactly what the target is and read those numbers, right? What is measured, but it would be good kind of to have the visual clue what the target is and how well we're meeting it.
Yeah, that makes sense. Yeah.
That said, uh, it would be interesting to find out additionally, what is the maximum data rate that this channel will work at, right? You have done this at 32 gig, but how far it will go? Will it go to 40, 50, 64? That will be interesting to see as well.
Yeah. Yeah.
There's an argument that the bit error rate number is a ridiculous number, and you really want to go for something which is, sort of, more of the 10 to the minus 1 to the minus 10 kind of minus 8 level.
Mm.
There's a trade-off in how many resends and stuff you have to do.
Yeah.
Right. Yeah. But right. Again, if UC says, hey, yes, there is a trade-off, but the question is, what is the baseline, right? How do we meet
There's not really,
baseline?
yeah. Are you saying a baseline for a given bit error rate?
Yes, right. Basically, the UC will tell you, hey, you have to have this much bit error rate, and this is the window which you have to hit for this bit error rate, and we are comparing against that.
Yeah.
But I agree, right? Obviously, right? If you're meeting 10 to the minus 15, if you're not meeting 10 to the minus 15, but you're meeting 10 to the minus 14, that's a trade-off that definitely a designer can make.
Yeah, I mean, some of what we're trying to do in the Open Atomic Ethernet, or I'm trying to do it anyway, is say, okay, if you've got a couple of crappy channels or a few crappy channels, do they aggregate it together, give you the bit error rate equivalent you need?
Oh,
So
yeah.
there's kind of trade-offs, which if the chiplet can't do minus 10, 10 to the minus 11, do you have enough channels that'll get the throughput I want, on something else? But so there's a three-dimensional space here.
Yeah, right. Yeah. But by the way, in this picture, I also got confused as well. Actually, I got confused. So the number which you see on the right, the E minus 11, that's not the bit error rate. That's the width of the eye at the target bit error rate.
Yeah.
Right.
That looks a nice clean one, but so I'm looking at stuff where it's like that's probably way cleaner than it needs to be.
Yeah.
You kind of want
Again,
to push trade-offs.
yeah,
And so there's kind
obvious.
of, I'm saying there's more of like a three-dimensional surface here that you want to see.
Yeah.
Of things.
Yeah.
Pick the one you want.
Yeah.
Sorry, I
Agree.
might be derailing things there.
Yeah. And segment, this is with 2 line space.
Oh yeah, this is actually two line spacing. Oh, I forgot to change the registers.
Yeah, it's okay. Yeah.
Yeah.
Yeah. Kevin, we have one that's actually looking even better than that, but it's with one micron line width and 3 micron line space. So yeah, I agree that, yeah, see, this looks even better.
Mhm. Yeah. Yeah. So are at the UCA requirements on the graph, and
Yeah.
and I'm also planning to, as I discussed yesterday, I'm planning to do the CPU to HBM routing as well.
Yeah. Let's see how that looks. For that one, we'll try to do the staggered, both horizontally and vertically staggered routing. I've seen in IBM papers and other papers. That's pretty much the only way to get the density. I mean, the routing density to route all these gazillions of wires. So let's see how that looks. That's going to be our real challenge. Maybe we'll see how that looks.
Yeah. Let's see.
Yeah.
So that's all on my side.
Yeah. This is good stuff. We should start adding the stuff to the slides and be ready. So remember, I think September 25th was when we're supposed to have the final versions of our slides, I call them final drafts. Obviously, right? We have so this year the way Sigmund, the way the presentation is going to go is there will be all presentations are going to be on one computer, and everybody's going to be working out of that one computer.
Yeah, so that means we can modify slides until the last moment. And
well, yeah, the last moment is definitely not going to be the day before the presentation. Probably we should give everybody a few days to update the slides. So probably the Friday before the summit is our last chance to make any final changes. Right.
Gotcha.
After that, even if we send the slides, it's not guaranteed that people will be able to will have the time to take those slides and put them in the right folder. Right. So we could do that. The risk is that we're not going to have the latest slides. So that happened to me once. The reason I'm saying that is it happened to me once where I thought I'm going to be presenting one slides, and right in the middle of the presentation, I realized these are the old slides, so I had to scramble, threw off my cadence a little bit. But yeah.
Yeah, that makes sense. Yeah.
Okay.
Yeah.
All right. Good stuff. Let's see. Let's continue working on this. We'll sync up again next week to see how things are going. And
yeah, sounds good.
Yeah. Any comments from anybody? Boone, what do you think? Actually, let me show you guys the IO chiplet I'm thinking about, and let's see if let me show you this. Okay, so this is the IO chiplet, and basically Sigmund, I took your basically I took your setup for the CPU chiplet, and the UCEs on the bottom, and I just kind of shrank it and added the PCEs on top. And I think I have the bump map right now.
Oh.
My next order of business is to add this to the floor plan for the for here. All right, I'll add it just here on top. I'll add 4 on top, 4 on bottom, and hook it up. I think I kept the order correctly for the UCE, so I should be able to connect the connection to UCE between the CPU and the IO chiplet is going to be straightforward, meaning right to create the netlist. So you don't have to update your floor plan right now, but at some point we'll update it.
Yeah.
Yeah, and I have the power for that. It maxes out at 395 watts. And no, sorry, 438 watts, including losses in the so for the regulators, I just created one that I assume it has 95% efficiency. So you can see the 48, actually, this is the 48 to 12. It loses 20 watts. The 12 to 5 loses another 20 watts of power. And then on the PCB, they're okay. This is the UCE. UCE doesn't have a whole lot of power, but here's the core regulator. It loses another 20 watts. So we just have 60 volts out of the regulators. Oh, one thing is I added the HBM power as well, but I need to propagate that to the datasheet. I didn't know any better. So ChatGPT told me that I should use 20 watts of HBM4 power. And that's what I'm using. So that's going to be another, for HBMs at 20 watts, that's going to be another 80 watts. So this should be interesting to see what the total power looks like. Okay.
Yeah.
Any comments from you guys? Boone, Kevin? All right.
I'm still thinking back to your eye diagram thing. I was thinking it would be nice to have a more three-dimensional space graph of how the SerDes performs as you run it over its entire range, and then like you could pick out a box which is your particular protocol, you know, like UCIe. You know, the UCIe behavior you're asking for is in this box, and the total behavior of the SerDes.
Yeah, so when you say 3D space, you mean data rate over I, the
Yeah,
dimension?
you got like, you know, speed, voltage, or power, you know, things like that.
Yeah.
So
Right.
if you're selling a piece of SerDes IP, it's generally, you know, multi-use.
Yes.
Okay, the piece that if you're doing UCIe, you want to use this area, you know, of it, but you know, it works outside that if you want it, you know, kind of deal.
Yeah.
Just a thought. For the power stuff, I stuck I don't know if anybody's interested. I shoot video for the IEEE Pals group. There was an interesting talk about some of that 48 volt and down stuff.
Okay.
USB cables.
Yeah.
I put the chat in the put the link in the chat.
Yeah.
It's just that there's a lot of complexity in getting the power from 48 volts down to 1.
Yes. Yeah. And what's worse is the NVIDIA stuff is 400 volts. Next one is going to be 800 volts. So converting down to actually it's not even to 1.
There's, you know, there's ways to do things like that. So if you're doing HVDC for, like, you know, if you try to do megavolt power lines, you do it as a stack. So you have a big stack of semiconductor things that were working at kilovolts each rather than megavolts.
Yeah.
And you could, in theory, do the same thing with a rack, where you just say, I'm going to have all these servers and they're going to consume the same level of power. So I can just stack them. Each one's doing 48 volts, but you know, add them together, it comes to 800. You know.
Yeah.
And that's a fairly easy way to do it.
Yeah.
But power electronics is one of those weird things that not many people actually do.
Yeah, that's true.
And you'll run into Schneider repeatedly if you do it.
Yep. Yeah. All right. Okay. So we'll resume next week then. You guys have a nice weekend.
And here,
Bye.
Bye.